Dive, where we take your source material, your dense articles, your research, your notes, and we cut right to the core of what you need to know, giving you that rapid foundational expertise.
Today, we are strapping in for the ultimate trip. A deep dive into the very fabric of existence, or, at least our current best description of it. We are tackling the standard model of the universe, known officially as Lambda CDM or CDM.
The mission today is crucial. We're unpacking this model, and we need to recognize its near-perfect quantitative triumphs. I mean, it's often called the concordance cosmology for a reason, right? It unifies nearly all major observations.
It really does.
So critically, we're also highlighting the profound, staggering gaps it leaves wide open. The sources you shared paint a picture of a cosmos that is, on one hand, incredibly well measured, but on the other, just overwhelmingly mysterious.
It is the absolute pinnacle of current cosmological understanding. The foundational assumption, the bedrock that CDM is built on, is that Einstein's general theory of relativity holds true, even across these vast, almost incomprehensible scales of the universe.
And so far, that assumption holds up.
It does. And this model is currently, it's the simplest framework that successfully explains key phenomena. Things like the subtle temperature variations in the cosmic microwave background, the residual afterglow of the Big Bang.
The baby picture of the universe.
Exactly. And also how things like galaxies and galaxy clusters actually manage to form over cosmic time.
And the success of the model is exactly what makes the central mystery so acute. So let's establish the mind-boggling premise right off the bat, because this is the aha moment that really redefines how you perceive physical reality. The SCDM model requires, not suggests, but requires that 95.1% of all the mass and energy in the universe is made up of components we cannot directly see or fully understand.
Yeah.
We're talking about dark energy and cold dark matter.
We have spent centuries, millennia even, analyzing and theorizing about the 4.9%, the atoms, the light, the stars, everything we see.
All of human knowledge.
All of it. We know vastly more about that tiny fraction than we do about the 95.1% that actually controls the universe's large-scale architecture and ultimately its fate.
CDM is the best tool we have because it successfully calculates the effects of this invisible majority, but it fundamentally admits we're ignorant about their true physical nature.
So the model works, but we don't know why it works.
In a way, yes. This 95.1% is the central puzzle piece we are trying to force into place.
Okay, let's unpack this cosmic inventory then. If we were to calculate the energy budget of the entire cosmos, how does the model allocate the funds? The prevailing evidence, and this comes specifically from the detailed mapping of the CMB, tells us the universe is spatially flat, which means that on the largest scales, geometry behaves exactly as you would expect. Parallel lines never meet. And the flatness of the universe is a crucial constraint. It really is. It means the total energy density must exactly equal a very specific value, what we call the critical density, which is defined by the expansion rate.
Okay.
So the CDM is essentially the breakdown of that critical density into its three core constituent parts. And the dominance of the unseen is, it's impossible to overstate.
So give us the breakdown, starting with the largest item on the list. What are the percentages?
The largest chunk, the one dominating everything else, is dark energy. In the model, that's the lambda, the Alma. That accounts for a massive 68.3% of the total mass energy density.
68.3. So nearly 7 out of every 10 parts of the universe is this invisible, repulsive force. That's just staggering. What do we actually mean by dark energy in this CDM context?
Within the standard model, dark energy is. It's synonymous with the cosmological constant with lambda. It has a very strange property. It doesn't dilute as space expands. It represents a constant static energy density that's intrinsic to the vacuum of space itself.
Wait, break that down.
Okay, imagine you have a box of empty space. As you make that box bigger, the density of any matter inside it drops because the particles are spreading out.
Right, that makes sense.
But the density of the vacuum energy or dark energy remains completely constant. You get more space, you get more vacuum energy, the density stays the same.
So as the universe expands, dark energy becomes proportionally more powerful just because the density of everything else is dropping.
Precisely. Its role is absolutely central. It drives the accelerating expansion of the cosmos. It doesn't cluster, it's uniform throughout space, and its density relative to matter is what sets the stage for the universe's transition to, accelerated growth.
And what about the second largest component, the gravitational scaffolding we keep mentioning?
That would be cold dark matter, or CDM, which makes up 26.8%. And its name tells you pretty much everything about its nature. It's dark because it does not interact with electromagnetic radiation, doesn't emit, absorb, or reflect light. It's completely invisible.
Okay, so we can't see it.
And it's matter because it has mass and it interacts solely through gravity. It pulls things together.
Why the cold? That term seems pretty critical to how the model functions.
Oh, it is absolutely critical. Cold refers to its velocity. It must be slow-moving or non-relativistic. If dark matter particles were hot, like say neutrinos, they would have extremely high kinetic energy, which would prevent them from clustering effectively on small scales.
They would just zip around too fast to clump together.
Exactly. They would smooth out the early universe, essentially erasing the tiny density fluctuations that were needed to seed structure. But to form the intricate galactic structures we see today, you need these deep gravitational wells that stabilize very early on, attracting ordinary matter.
You need something slow and heavy.
You need slow-moving particles that can quickly collapse into these dense structures. Therefore, the CDM model stipulates cold dark matter to provide that gravitational scaffolding necessary for galaxy and cluster formation. Without that massive, invisible 26.8% pulling things together, the 4.9% of ordinary matter just wouldn't have had enough time since the Big Bang to clump into the magnificent structures we observe today.
And finally, the stuff we actually know and love. Ordinary matter or baryonic matter.
That is the small minority, clocking in at a mere 4.9%. This component includes all protons and neutrons, so everything made of atoms. Stars, planets, gas clouds, dust, galaxies.
And us.
And us. Life itself. Every telescope, every chemical reaction, every biological process is confined to less than 5% of the universe's total inventory.
That structural imbalance is just astounding. If you calculate the gravitational importance for galaxy formation, the 26.8% of cold dark matter is almost 5.5 times more important than the 4.9% of ordinary matter. The entire structure of the cosmos is defined by entities we can only detect through their gravitational influence.
It forces us to acknowledge that our current cosmological model is fundamentally a model of the unknown universe. The triumph of SCDM isn't that it solved the mystery of existence, but that it created this mathematically precise framework that successfully calculates the gravitational and energy requirements of that invisible 95.1% to match every single observation we make.
So if I'm hearing this correctly, the 26.8% of cold dark matter dictates the architecture, the skeleton, and the 68.3% of dark energy dictates the destiny, the ultimate expansion of the tiny 4.9% of the matter we can actually see.
That is a perfect synthesis of the cosmic inventory.
Okay, so we've established the inventory. Now we shift our focus to the largest, most powerful component, dark energy, the 68.3% that defines the future. And here's where it gets really, really interesting. Dark energy is not just some passive filling. It's an active, repulsive force that ensures the universe will never stop expanding.
This brings us back to the revolutionary insight that was confirmed in the late 1990s. Dark energy, the lambda component, has a defining and frankly bizarre physical property that creates a repulsive gravitational effect. It has negative pressure.
Negative pressure. In standard physics, pressure is generated by kinetic energy, particles bouncing around, which actually adds to gravity's attractive pull. So how does negative pressure translate into anti-gravity?
This is a deep dive into general relativity. In GR, gravity responds not just to mass energy density, which we call rho dodico, but also to pressure, which we call d may. Normal matter has positive pressure, which actually generates even more attractive gravity.
So more pressure, more gravity.
Right. But dark energy, which we associate with the cosmological constant, follows a very specific equation of state. PP equals rho C22.
The pressure is the negative of the energy density.
Exactly. Imagine a stretched spring or a rubber band under incredible tension. That tension, that negative pressure, is an outward pushing force. This extremely negative pressure is what provides the necessary repulsive gravitational effect. So as space tries to contract due to the attractive gravity of matter, the vacuum energy resists that contraction with this massive continuous outward push.
So it's not like an explosion pushing outward, it's the vacuum itself exerting this continuous tension.
It acts fundamentally as a gravitational repellent. It's what ensures the accelerated expansion of the cosmos.
That's a crucial distinction. And speaking of the cosmological constant, we have to mention the history here. When did this idea of lambda first even enter cosmology?
Well, the cosmological constant has a famously checkered history, originating with Albert Einstein himself. When Einstein first formulated general relativity back in 1917, his equations suggested the universe should either be expanding or contracting.
But everyone at the time thought it was static.
The prevailing view, yes, held that the universe was static and eternal. So Einstein needed a term to counterbalance gravity and ensure a stable, unchanging universe.
So he essentially just shoehorned in this repulsive force to keep the universe from collapsing on itself.
He added lambda to his field equations for that exact purpose. Then, about a decade later, Edwin Hubble proved observationally that the universe was expanding.
Whoops.
Yeah. Einstein subsequently retracted lambda, and he famously called it his biggest blunder.
The ultimate cosmological irony. He introduced lambda to ensure a static universe, only for it to be observationally confirmed as the key driver of an accelerating universe 8 decades later.
The observation of accelerated expansion in 1998, which brought lambda back from the dead, showed that Einstein's original equation, with lambda included, was actually the correct description of the universe, just not for the reason he first intended.
So how did we know for certain in 1998 that the acceleration was real? What was the observational proof that resurrected Einstein's constant?
The crucial evidence came from 2 independent teams measuring type Ia supernovae, SNIA for short. These events are the spectacular explosions of white dwarf stars that reach a very specific critical mass.
Okay.
Because they all explode under very similar circumstances, they serve as remarkably reliable standard candles. We know their absolute intrinsic brightness.
And if you know how bright something truly is, measuring how dim it appears tells you its exact distance. It's a simple inverse square law.
Exactly. So by measuring the redshift, which tells you how fast a galaxy is moving away from us, and then measuring the distance using the SNIA brightness, cosmologists could plot the expansion history of the universe.
And what did they find?
What they found was shocking. Distant supernovae were significantly dimmer than they should have been if the universe were expanding at a constant or slowing rate.
Meaning they were farther away than the redshift suggested they should be.
Yes. The space between us and those distant galaxies had expanded more than expected over the intervening time. This could only be explained if the expansion rate of the universe had not been constant, but had been speeding up, accelerating for the last several billion years. This was the unmistakable sign that dark energy's repulsive effect had become the dominant force in the cosmos.
Wow. That sounds like the ultimate cosmic shift. When did this transition happen? When did dark energy finally win the battle against matter's gravity?
Well, early in the universe's history, the density of matter, both ordinary and dark, was extremely high. In that matter-dominated era, gravity was the overwhelming force, and it was causing the expansion to slow down.
Like throwing a ball up in the air, gravity's pulling it back?
A perfect analogy. However, as the universe expanded, the density of matter decreased rapidly. But remember, dark energy density, being intrinsic to the vacuum, remains relatively constant.
So there was a tipping point.
Yes. The transition point occurred roughly 5 to 6 billion years ago. Once the matter density dropped below the threshold of the constant dark energy density, dark energy's repulsive push became the dominant force, and that initiated the phase of accelerated expansion we observe today.
The universe went from braking to hitting the gas pedal.
That's a great way to put it.
So the ACDM model, constrained by data primarily from the Planck CMB mission, offered an extremely precise picture of this history. Let's look at the key parameters derived from these early universe observations.
The precision is just astonishing. ACDM gives us a highly constrained view of cosmic history. For instance, the model pinpoints the age of the universe at 13.787 PM.020 times 199 years.
Plus or minus just 20 million years out of nearly 14 billion. That margin of error alone is a powerful testament to the model's self-consistency.
It really is.
And the other critical number, the current speed of expansion, the Hubble constant, h$, is derived from that Planck data, which models the infant universe's structure.
Based on the physics established during the recombination era, when the CMB was formed, the ICDM framework calculates the predicted value to be 67.4 PM1 text 2 undone.
Okay, let's break that unit down. For every megaparsec, which is about 3.26 million light years further away a galaxy is, it recedes from us an additional 67.4 kilometers per second.
Correct. This 67.4 number is the bedrock prediction of the Standard Model, based on the physics of the early universe.
We absolutely must keep that 67.4 number firmly in mind as we transition to the tensions, but first let's address the implications for our cosmic future. If we have a universe dominated by this constant repulsive energy, what does ACDM predict for the ultimate fate of everything?
The domination of dark energy with a positive cosmological constant that doesn't dissipate implies a definitive and frankly a cold outcome. The universe will expand forever. The repulsive force is simply too great for gravity to ever slow, halt, or reverse the expansion. We are not heading toward a big crunch.
So no collapse. And what does expanding forever look like on unimaginable timescales?
The most probable scenario is what we call the big freeze, or the heat death of the universe. As the expansion accelerates, everything outside our local galactic cluster will eventually recede faster than the speed of light, effectively disappearing from our observable horizon.
So the night sky will eventually go dark.
Completely dark, except for the members of our own local group of galaxies. Over eons, all the stars will burn out, leaving black holes that will themselves eventually evaporate through Hawking radiation, and then just an extremely dilute soup of fundamental particles. The universe will approach a state of maximum entropy and thermal equilibrium.
Uniform, cold, and dark.
Forever. The accelerating expansion isolates us, guaranteeing a lonely, frozen infinity. It is perhaps the most chilling prediction of the entire model.
We've established TDM as this incredibly successful, precise model. It explains structure, it explains the CMB, it predicts the age, and it describes this future of eternal expansion. But here is the critical pivot point of our deep dive. Despite its quantitative successes, the model is facing challenges. Serious challenges, not just observational, but deep theoretical impossibilities that suggest ACDM is at best incomplete, or at worst, fundamentally flawed.
And these are not minor statistical noise. These are profound cracks in the foundation. They represent significant discrepancies between what the model predicts based on early universe data and what we can measure directly in the late or local universe. To resolve these tensions, as they're called, requires venturing into the territory of entirely new physics.
Let's start with the most noticeable conflict right now, the one that truly pits the baby universe against the adult universe, the Hubble tension.
The Hubble tension is the conflict over the precise value of $1,000,000,000. The Hubble constant. As we just discussed, the value derived from the early universe physics, specifically the Planck mission's analysis of the cosmic microwave background, which sets all the TCDM parameters, is approximately $67.04 positive text kill SMP say.
Okay, that's the prediction.
That is the predicted rate of expansion based on the model's consistent history, flowing from the Big Bang forward.
But when cosmologists look at the local late universe using direct astronomical measurements, they get a different number. We are literally watching things expand now, and that rate doesn't match the prediction.
That's the entire crux of the conflict. Local measurements rely on constructing what's called the cosmic distance ladder. This is a rigorous, multi-step process for measuring absolute distances in the nearby universe and then using those to calibrate distances farther and farther away.
Okay, let's unpack that ladder for the listener. What are the rungs?
The first rung involves direct geometric measurements using parallax, the apparent shift of nearby stars as Earth moves around the Sun. It's simple trigonometry, and it gives us extremely precise distances to those nearby stars.
Okay, the foundation of the ladder.
The second rung uses those stellar distances to calibrate the intrinsic brightness of Cepheid variable stars.
Ah, Cepheids. They're fantastic because their pulsation period, how fast they brighten and dim, is directly linked to their absolute brightness. So measure the period, you know the true brightness, you measure the apparent brightness, and bingo, you get the distance.
Exactly. And Cepheids are bright enough that they allow us to reach out to nearby galaxies.
So they get us off our island, so to speak.
Precisely. And the third and final crucial rung uses the calibrated Cepheid distances in those nearby galaxies to then calibrate the absolute brightness of the Type Ia supernovae we discussed earlier, our standard candles.
And since those supernovae are so incredibly luminous, they can be seen billions of light years away,
allowing us to measure the expansion rate across vast cosmic distances in the here and now.
So when this entire cosmic distance ladder is built and used to calculate the Hubble constant, what value do the local observers consistently arrive at?
The value consistently comes out significantly higher, clustering robustly around $73 in text-Kelm MP. The most precise late universe measurements are typically in the range of $73 to $73 to $73 Kelm MPP.
Okay, let's be crystal clear for the listener. We have two completely different independent methodologies. One based on modeling the baby universe from 380,000 years after the Big Bang, which gives us 67.4.
The CMB prediction.
And another based on directly measuring the adult local universe right now, which gives us 73. And they fundamentally disagree about the universe's current growth rate by almost 10%. That seems catastrophic for a concordance model.
It is a profound statistical discrepancy. When you combine the various local measurements, the difference is statistically significant, often exceeding 4 or even 5 standard deviations. In particle physics, 5 sigma is the gold standard for a discovery. Here, it signals a crisis.
And the certainty's only getting stronger, isn't it?
It is. The accuracy of those local measurements has only been reinforced. Data from the James Webb Space Telescope has helped reduce systematic errors in the distance ladder, particularly with the Cepheid measurements, strengthening the certainty that 73 is the correct local rate. It's increasingly difficult to just dismiss this tension as some simple measurement error.
So if the model, based on early physics, predicts 67.4, but the current reality is 73, what does this signal? We need new physics. New physics where, exactly?
It signals that the SCDM model is missing a phase of the universe's expansion history. The most popular solutions involve modifications in the very early universe, sometimes called early dark energy, or EDE.
Early dark energy, how would that solve this?
Well, if a new component, perhaps a temporary scalar field or a modified form of dark energy like quintessence, was briefly dominant or more energetic than predicted in the very early universe, it would cause the universe to expand faster than the standard CDM model allows in that period.
So a sort of brief, early cosmic speed boost.
Exactly. That early, faster expansion would influence the acoustic oscillations recorded in the CMB, the size of the sound horizon, and it would require us to retune the other parameters of the SCDM model to fit the CMB data.
I see.
If we put that early boost into the model, the predicted d Joule-Wheeler value that we derive from the CMB would naturally come out higher, potentially increasing it from 67.4 up toward the observed 73, closing the gap.
So the Hubble tension isn't just about disagreeing numbers, it's a clue. It suggests there might have been a hidden event in cosmic history, an additional ingredient present only in the first fractures of a second, that the current standard model is simply missing.
That's right. It's forcing us to acknowledge that the concordance model, while functional, might be the wrong physical description of the universe across all epochs.
Okay, if the Hubble tension is the observational challenge, the cosmological constant problem is the theoretical one, and this is where physics just hits a wall. This tension isn't about two numbers disagreeing by 10%. It's about theory failing to match reality by an impossible, almost comical margin. It is, as you said, one of the biggest embarrassments in modern physics.
This is truly the philosophical crisis at the heart of ACDM. So, we established that dark energy is associated with the energy density of the vacuum itself. We have the two pillars of modern physics: general relativity, which governs the large-scale universe and gravity, and quantum mechanics, specifically quantum field theory, or QFT, which governs the microscopic behavior of particles.
And when cosmologists try to use QFT to calculate the energy density of the vacuum, they are calculating the zero-point energy, right? The energy that persists even when a region of space is completely empty of matter and photons?
Yeah, that's correct. Quantum mechanics dictates that even a perfect vacuum is seething with virtual particles popping in and out of existence, and each of these fluctuations contributes energy. When you try to sum up all the potential zero-point energy contributed by every known particle field, electromagnetic, weak, and so on, the theoretical result is staggeringly large.
How large is the discrepancy?
The theoretical calculations based on quantum field theory suggest the vacuum energy density should be approximately 10 times greater than the density we actually observe in the form of dark energy.
Okay, let's just pause on that number because it is impossible to grasp casually. A 1 with 120 zeros after it. The entire observable universe contains roughly 10 fundamental particles.
Correct.
That means the theoretical vacuum energy is not just a little off, it's the energy of the universe we know, multiplied by the universe we know, and then multiplied by itself billions and billions of times again. If that prediction were even remotely correct, what would have happened to the universe?
If the quantum prediction for vacuum energy were accurate, the gravitational pull generated by that enormous density would have been so immense that the universe would have collapsed back in on itself almost instantaneously after the Big Bang, long before any stars or galaxies could form.
So the universe would have been a footnote.
It wouldn't even existed for a Planck time. The fact that the universe exists and is expanding at all proves empirically that the QFT prediction is massively fundamentally wrong.
So the very existence of our cosmos requires some hidden, completely unknown mechanism that causes 99.999 with 129% of the theoretical vacuum energy to cancel itself out with exquisite, almost perfect precision.
That is the core of the cosmological constant problem. And CDM sidesteps this theoretical catastrophe entirely. It simply states, we observe a tiny residual cosmological constant, and we will use that observed value as a parameter in our equations. But it offers absolutely zero physical or theoretical explanation for the required cancellation.
It's an admission that the two greatest theories in physics, general relativity, and quantum mechanics are fundamentally incompatible on the specific existential point.
It represents the most dramatic conflict in science. Solving the tenor discrepancy would require a truly unified theory of quantum gravity, something that resolved the behavior of energy at the microscale with the gravitational consequences at the macro scale. Until that happens, CTDM remains successful, but theoretically unstable.
We move now from the theoretical crisis of quantum gravity to the empirical failures of our required dark particle-cold dark matter. If 26.8% of the universe is CDM, and it's the skeleton upon which everything hangs, why are we still questioning it?
The questioning arises because, unlike dark energy, which we confirmed through acceleration, the existence of cold dark matter is confirmed purely through its gravitational effects on visible matter and background radiation, its physical reality as a particle. Well, that has not been confirmed. It is a necessary hypothetical ingredient.
And the simplest, most popular hypothesis for what dark matter is made of are WIMPs, right?
WIMPs, yes. Weakly interacting massive particles. This is the cold hypothesis. WIMPs are theoretically heavy, slow-moving particles that interact only through gravity and possibly the weak nuclear force. They are the ideal candidate because their properties naturally provide the right density, the 26.8% required by CDM, and they're heavy enough to cluster early.
They're the perfect scaffolding material.
On paper, yes. Yet years and years of increasingly sensitive experiments trying to catch WIMPs passing through the Earth haven't yielded any positive results.
That is the first major issue, isn't it? Direct detection failure.
It is. We have experiments deep underground, shielded from cosmic rays, that are essentially just trying to catch a WIMP colliding with an atomic nucleus and creating a tiny detectable recoil signal.
A tiny ping.
Exactly. And while the search continues, the non-detection has forced cosmologists and particle physicists to systematically rule out the simplest and most plausible WIMP models. This casts a serious shadow on the cold part of CDM. If they aren't WIMPs, what are they? Axions, sterile neutrinos. The lack of a smoking gun particle means the scaffolding material is still completely unknown.
And beyond the particle physics failure, the model also seems to struggle with simulating the structures CDM is supposed to create, especially on the smallest scales.
That's the second set of problems, often called the small-scale crisis. Standard CDM simulations, which really only include gravity and non-interacting cold particles, produce structures that clash with detailed astronomical observations of real galaxies.
What's the first clash? The halo density problem.
Right, the halo density problem, or as it's sometimes called, the cusp core problem. CDM simulations predict that galactic halos, the massive invisible dark matter structures surrounding galaxies, should have a very sharp density spike at their centers, a gravitational cusp.
A very steep density profile right at the very center of the galaxy.
Yes. However, when astronomers observe the rotation curves of many dwarf and low surface brightness galaxies, they often find halos with much shallower density profiles. Essentially, they find a flat core rather than a sharp cusp.
So the dark matter is spread out more than predicted.
It appears to be distributed more smoothly and uniformly near the center than the cold, non-interacting nature of standard CDM predicts. Observations of dwarf galaxies like Fornax or Sculptor consistently show this flatter core density.
And then there's the missing satellites problem, or dwarf galaxy problem.
This is a profound demographic issue. CDM simulations, based on the sheer mass of dark matter halos, predict that a massive halo like the one surrounding our own Milky Way should host a hierarchy of thousands upon thousands of smaller subhalos.
And each of those should be able to form a dwarf satellite galaxy.
Right. The model predicts a huge number of potential homes for dwarf galaxies.
But how many do we actually observe around the Milky Way?
We observe only a few dozen, around 60 known satellite galaxies at last count. The model predicts that for every observed dwarf galaxy, there should be dozens or even hundreds of unobserved dark matter-dominated satellites. Even if you account for galaxies that are too dim for us to see, the discrepancy between the simulated inventory and the observed inventory is enormous.
So we have a structural model where the required building blocks can't be found, the WIMPs and the resulting architecture, the central cores, and the number of small satellites doesn't match the blueprints. This is pretty strong evidence that dark matter might not be perfectly cold after all.
It suggests we need to modify CDM. Perhaps dark matter is warm, WDM, meaning the particles are slightly faster, which would smooth out the structure and prevent the formation of all those small halos. Or perhaps dark matter is self-interacting, SIDM, meaning the particles occasionally collide with each other, which would naturally push them out of the center of a galaxy and create those observed core density profiles instead of cusps.
So the problem isn't necessarily dark matter itself, but the cold part.
The success of CDM forces us to accept dark matter in some form, but the details of structural formation force us to question its cold, non-interacting designation.
And finally, there's the F-AHO tension.
Yes, finally, we should briefly mention the A-state tension. This is another purely observational discrepancy. It's analogous to the Hubble tension, but it concerns the distribution of matter itself in the late universe, rather than its expansion rate.
So how clumpy is matter distribution now versus how clumpy the early universe data suggests it should be?
Exactly. Say-state HN is a parameter that quantifies the clumpiness or the amplitude of matter fluctuations in the universe. If the universe has a high A-state value, it means matter is very clumpy and structure formation has been vigorous. If it's lower, structure formation has been slower or less pronounced.
How do cosmologists even measure this clumpiness in the late universe?
Primarily through large-scale surveys that utilize a technique called weak gravitational lensing. This involves measuring the subtle distortion of light from distant background galaxies as it passes through the mass distributions, galaxies, clusters, and their intervening dark matter halos in the foreground.
So you're using light as a probe.
The degree of the light distortion tells you precisely how much matter is clustered there.
And what does that local measurement tell us compared to the CMB prediction from Planck?
The local measurements from these lensing surveys, like the Dark Energy Survey or KIDS, suggest a slightly lower amplitude of matter fluctuations. The universe appears slightly less clumpy than what is predicted by the Planck CMB data using the standard CNEM parameters.
How significant is it?
The SICN8 value derived from late universe measurements is consistently 2 to 3 standard deviations lower than the CMB prediction. It's not at the crisis level of the Hubble tension, but it's another measurement where the model derived from the infant universe seems to slightly overpredict the vigor of the adult universe's growth.
It's another piece of the puzzle that doesn't quite fit.
It acts as a powerful cumulative hint. When you combine the H$ tension, where the universe is expanding too fast, and the 88 jet tension, where it's clumping slightly too slowly, you see a consistent pattern. The universe in its later stages appears to be slightly different than the model derived from its infancy would suggest.
That seems really significant.
It strongly reinforces the idea that we're missing an element of physics that subtly bridges the early and late cosmic epochs. It could be a modification to gravity or an interaction involving dark energy or dark matter that changes over time.
So we started this deep dive with the ADCDM model as the concordance cosmology, a quantitative triumph that accurately describes the universe's evolution, structure, and fate. It gives us the age, the expansion rate, the percentage breakdown of existence. It's an incredible achievement.
And we end with the recognition that this incredibly precise description is built on a foundation of monumental unknowns. ACDM is mathematically robust, it works incredibly well, but it is conceptually incomplete. It accounts for the effects of dark energy and dark matter to match observations, yet it leaves open the most profound questions about their true nature and the fundamental forces governing our universe.
What stands out to me is just the staggering audacity of the numbers. The model requires 95.1% of the cosmos to be entities we cannot interact with or understand, forcing us to essentially rename our ignorance. And then you have that theoretical conflict, the one that pits gravity against quantum theory, yielding the tenement tripacy.
The standard model is a magnificent 6-parameter model that explains the history of the universe. Yet it operates entirely over this chasm of fundamental ignorance. It tells us what the structure is, but not why 95% of it behaves the way it does, nor how vacuum energy manages to cancel itself out with such absurd, impossible precision.
And the tensions are the cracks showing.
The tensions we discussed, Hubble, $6087, and the CDM particle and structure issues, are the observational symptoms that something more complex is happening than the standard 6-parameter CDM model allows.
The deep dive suggests that the search for what the universe truly is has really only just begun. So here is the final provocative thought for you to chew on. The model, in its current form, essentially assumes dark energy and dark matter are entirely separate, non-interacting entities. But what if the solution to the Hubble tension, which might require early dark energy, and the solution to the cosmological constant problem, which requires this perfect cancellation, are actually two symptoms of the same fundamental unknown force. It suggests the next great leap in cosmology won't just be finding a new particle, but finding an entirely new framework for existence. A theory where dark energy and dark matter might actually be linked and perhaps even interact with each other, fundamentally rewriting our understanding of gravity and quantum mechanics across the entire cosmos. That unified theory is out there, waiting to be discovered. Welcome back to The Deep Dive, where we take your source material